In 1.2, we're going to look at relations and functions. The first thing that we're going to discuss is going to be set builder notation and interval notation. In our prior sections, we had talked about set builder notation. So what we're going to do now is we're going to translate from set builder notation to interval notation, and also we're going to graph our sets on a number line. So let's look at what we call an open interval. An open interval in set builder notation using inequality symbols will look something like these first three examples. Remember, in set builder notation, we have our set braces, and then we're saying, okay, this is a set of all x. The bar means such that our x values are greater than a. And in this case, a is just any real number. So for example, I could say that x is greater than 1. So that would be our set builder notation. Now when we look at the interval notation, since our x values are strictly greater than our a value, that means that it cannot be equal to the a value. And in fact, if you look at all of these inequalities in set builder notation for the open intervals, it's always a greater than, a less than, but not an or equal to. So we indicate that it can be greater than our number a, but not equal to, by the use of a parenthesis. So the parenthesis means not equal, but can be bigger in this case. And x can be any number greater than a, so we're going to go all the way to infinity. But we can never reach infinity, so that's why we're going to have a parenthesis next to the infinity, because we can't get there. So anytime you have a negative or a positive infinity in set builder notation or in interval notation, it's going to be a parenthesis. In our example, we were saying that x was greater than 1, so if we're looking at that particular example, it would be 1, infinity. So this is a set. It's not an ordered pair like we did when we graphed points. This is a set where we can choose any value for x, 1 through infinity, but exclusive. We're excluding 1 and infinity. So how would we graph this? So we would graph this using that interval notation. We would just take that parenthesis, put it on our graph, and below it put our number a. In our case, our little example, we were using 1. And then since we're looking at x values strictly greater than our a value, we have to make sure that we shade everything larger than. So although we don't write it on our graph, that arrow at the end, that means we're going to positive infinity. Okay, so let's zoom out a little bit. We have our set builder notation, translate that to interval notation, translate that to a graph. In that same box, we have another case where we have an open interval. And now these are called open intervals because both ends of the interval notation have parentheses. So if you've got a set of parentheses, it's open. In this second example, we have x between some a and some b value. But it's strictly, x is strictly greater than a, x is strictly less than b, not equal to. So again, we're going to have parentheses, and we're going to look at all x values between a and b, not including a or b. And something that we have to be careful with interval notation is that we're always going from small to large. Order matters. So if we were to graph, we would just take that interval notation, parenthesis A, parenthesis B. We want to face the parentheses in the direction where the set is. And the last example for an open interval is when your x values are strictly less than some value, some real number value b. So less than means anything smaller than b, but not including b, so there's a parenthesis on b. Everything smaller, we're going to go to negative infinity. So again, remember parentheses whenever you have a negative or a positive infinity, because you can never reach it. And order matters. So negative infinity is the absolute smallest value, and it would be everything up until b, but not including b. So when we look at our graph, it's everything until b, but not including b, so we would have a parenthesis. So we're going to look at some other intervals. Let's look at this first one that says a set of all x such that x is greater than or equal to a. Because we have or equal to a, that means x can equal a. So in the case where we can include that value, we're going to use a bracket, not a parenthesis. So these are x values that can equal a, so we're going to have this bracket to indicate that we can equal a. And everything larger than, so it's going to go to positive infinity. And then if you look at the graph, translating that to a graph, very simple, you're just taking that interval notation, which would be a bracket, adding it to a graph. Now if you used to graph with the solid circle and the open circle, this bracket would be the solid, because it includes that value. And again, we always shade where the set is. Let's look at the next example. We're looking at x values that are strictly greater than a, but less than or equal to b. So strictly greater than a means cannot equal a, so parenthesis next to a. Less than or equal to b, can equal b, bracket. And then you see the corresponding graph would be the parenthesis, the bracket, and everything in between. Another example would be if we switch so that x is greater than or equal to a, but strictly less than b. So bracket next to the a, because we can include that in our set. Parenthesis next to b, translate to the graph, bracket, parenthesis, shade everything in between. Last example would be x less than or equal to some b value. So we can include the b value, which would be a bracket, and then everything smaller, we would have a negative infinity on the left. So remember, we're always going from small to large. And parenthesis next to infinity or negative infinity, bracket on the b for the graph, and everything smaller than. So we don't really have a name for those intervals because it's not two parentheses or a set of parentheses, so it's not open. We do have something called a closed interval though. Open interval has parentheses on both sides of the interval. Closed interval has brackets on both sides of the interval, and that only happens in one case. And that would be if your x values are greater than or equal to some real number, less than or equal to some real number. Because then we would have brackets on both sides, which would translate to brackets in the graph, shade everything in between. So that's the only example of closed. We also have something called a disjoint interval. A disjoint interval is when we have an or in our set. So in this case, look at this, says our x values are less than some a value, or our x values are greater than some b value. So remember, or in set notation is our union. And is an intersection, or is a union. So for this first one, where it says that x is less than a, we're going to write that in interval notation. So that would be this first interval. Less than a means a and everything's smaller. So it's going to go negative infinity, comma, a. Or would be the union symbol. And then my next interval would be x greater than b. So not equal to b means parenthesis, but everything larger would mean we're going to positive infinity. Again, look at those intervals. We're going from small to large. Even with the union, we're going negative infinity to some a value, union, b to positive infinity. When we look at the graph, we would have a parenthesis where the a value is because not equal to, and everything smaller. Or we can choose x values with b, everything larger. Now there are other examples of disjoint intervals. You could actually have a less than or equal to, greater than or equal to. It's disjoint because of the space between those two intervals on the number line. Now the special case where you're talking about all the real numbers, you just got to describe it in words. The set of all x such that x is a real number. Interval notation is just negative infinity to positive infinity. And then what you would be doing is you would be shading the whole number line, because it's any real number, it's everything. We'll practice that in example 1. We'll write each set using interval notation, and then we'll graph each set. In A, we have the set of all x such that x is greater than or equal to 1, but less than 10. So greater than or equal to 1 means we include 1, so we'd have a bracket, 1, comma, 10, but we're not including 10 because it's strictly less than 10, so that would be a parenthesis. So when I graph this, now whenever you graph using a number line, you don't have to do a million little tick marks and have the negatives and the 0 and the positive numbers. You just have to put the two numbers, in this case the two numbers that are listed. You would just need bracket 1, parenthesis, 10, but don't forget to shade, clearly shade everything in between. Just because you have a bracket and a parenthesis means nothing without that shading in between. Alright, let's look at B. The set of all x such that x is strictly less than negative 3. So since it's strictly less than negative 3, I know I'm going to have a parenthesis around the negative 3. And it's everything smaller than, so that's going to be negative infinity to negative 3 with parentheses. If I graph that, I only need one number because only one number appears in my interval, and that would be negative 3. So it's going to be a parenthesis where the negative 3 is, and everything less. Again, don't forget to clearly shade the region of your set. Without that, that negative 3 would just be like an open circle with nothing shaded on either side. It means nothing. Okay, so x greater than or equal to 5. Since it can be equal to 5, it's going to be a bracket. 5, comma, everything bigger would give me positive infinity, and my graph would be the only number I see is 5. So it's going to be bracket, 5, and everything else. Let's move on and talk about relations, domain, and range. When we talk about a relation is just simply a set of ordered pairs. Okay, so often when we write ordered pairs, we will write them as X and Y. So if you have a relation which is a set of ordered pairs, the X values would be your, what we call, domain. And the Y values, that second component in the ordered pair, would be the range. So the first thing should be your domain, the second value would be your range. Example 2 asks us to state the domain and range for our relation. So if we look at A, this is a relation, it's a set, and it's a set of ordered pairs. So remember, the X values would be your domain, and when we look at each ordered pair, the first element would be my X value. So -1, -2, -3, -3. If I were to list my domain, that would be equal to, it's a set, and I'm just going to list the different X values. So we have a -1, comma, -2, comma, -3. Notice that there's two -3s there. You only have to list it once because all it's saying in the domain is -3 is there. It doesn't matter how many times it's listed in the ordered pairs. The range, that's going to be your second component in the ordered pairs, or your Y value. So here this would be 1, 2, -3, +3. So 1, 2, -3, and +3. Now order doesn't matter, but typically you'll see that the solutions will have you list the elements from small to large. So maybe they would list the -3 first, but it really doesn't matter. Order only matters if you're trying to establish a pattern. So that would be domain and range. But now let's look at example B. Well, is this a relation? Is this a set of ordered pairs? Well, it may not look like a set of ordered pairs, but we do have X values and we have Y values. So I could, if I choose, write this as the set of, if we look at the first column, it's X is 1, Y is 1. So that would be the ordered pair 1, 1. And then the next column would be 2, 5. And then we have 3, -3, and then 4, 0. So I can write this table as a set of ordered pairs, so it is a relation. The nice thing about having your values written as a table is you can clearly see what your domain is. You just go along that first row, and the different X values would be 1, 2, 3, 4. And then the range would simply be the Y values. So if we go along the row with the Y's, it would be 1, 5, -3, and 0. So moving on, we're going to talk about what a function is. And a function is just a special type of relation. If we look at the definition here, we see that a function is a relation, but it's a very special relation, so that every element in the domain corresponds to exactly one element in the range. Well, that's a little bit difficult to understand. Let's just look at this diagram of what we call a function machine. So I have this function machine, and I'm going to put in an X value into my machine. Those X values will be chosen from a domain. So I'm going to take an X from my domain, I'm going to put it in the function. The function's going to do its job, and it's going to spit out one value, and that f with the parentheses x is the value or the output that comes out from my machine. And there's just one. We typically call this value y. And we're choosing y from we're not choosing y. We're actually getting a y value from the x value that we put in. And that would be our range. So what we put in comes from the domain. What comes out comes from the range. And in a function, every input, every x value has only one output. So it corresponds to only one y value. Something else that's going to come up is what we call our function notation. And this is something that I know you guys are all familiar with. So when we talk about our function notation, if y is a function of x, so in other words, if y depends on x, which is what we have in a function, right? The y value depends on what x value you put into your function. Then we can write y equal to f of x. Now the f with the parentheses x is not multiplication. It's function notation. It says that you're putting an x into your function f. So we call x the independent variable because we can choose whatever we want, any x value from our domain. But the y value is dependent on what x we put into our function. So y is dependent, x is independent. Example 3, we want to state the domain and range for the relation, and then we're going to determine if the relation is a function. Part A, we have this table. I can see what the domain is by just looking at this table. Ooh, I don't want green, I want blue. So my domain is the set. X is 1, 1, 3, 4, but I only have to list 1 once. So 1, 3, 4. That's the domain. And then the range is going to be the set of the y's, which would be 0, 2, 4, 6. So I have my domain and range. Is this a function? Well, no, it's not. This is not a function. And the reason is that, look at when x is 1. When x is 1, we have the same x value, but we have two different y values. To be a function, for every x value, you only get one y value. So in other words, when x is equal to 1, y is equal to 0 and 2. So I don't get one y value. That's why it's not a function. If you have a set of ordered pairs, or if you have a table that represents your relation, what you want to look for is x values that are the same. If you have all the x values different, it's automatically a function. But if you have x values that are the same, double check to make sure the y values are different. If the y values are different, it's not a function. Let's look at B. B is a little bit different. I haven't seen this yet. So this is a set. It's set builder notation. So let's go ahead and read this. This is the set of all ordered pairs x and y, such that, and then after such that, we're going to describe the relationship or the relation between x and y, such that y is equal to x plus 1. When you have an equation and you're trying to figure out domain and range, it can be a little bit difficult. Let's think about this. The domain. What we're going to do is we're just going to look at the equation, and we're going to ask ourselves, do I have a problem with any of the x values? So usually if x is in the denominator of a fraction, you know, denominators can't be equal to 0. Or if x is, say, underneath a square root, it can't be negative. In this case, when we look at our x, we can put in any real number. So our domain is going to be all real numbers. I can put in any value for x. I got no problem with negatives, positives, 0, nothing. Range is a little bit different because it depends on the x's that you put in. Well, let's think about this. If I put in any number for x, I'm just adding 1 to it. So my y's that I'm going to get back when I put in my x values will also be all real numbers. I'll get everything. Think about my domain. If I add 1 to negative infinity, it's still negative infinity. If I add 1 to positive infinity, it's still positive infinity. So my range in this case is also all real numbers, or the interval from negative infinity to positive infinity. And that is really tough to see when you don't have a table or a set of ordered pairs. So we'll look at another way that you can look at domain and range when you have an equation in just a bit. But let's determine if this is a function. Now remember, for every x I put in, I should just get 1 y back. So if you look at this equation and you think about putting in some number for x, you're just going to add 1 to it, and then how many y's are on the other side of the equal sign? I just see 1. It's not like y squared. So it says you're going to put it in an x, you're going to add 1 to it, and then you're just going to get 1 y value back. So in an equation, if you can get the y by itself on one side of the equal sign equal to a single expression on the other side of the equal sign, then it should be a function. Okay, so this is, yes, it is a function. I put in an x value, I just get 1 y value back. Again, it's a little bit more difficult to see when you're looking at an equation and not a table or a set of values. So before we look at domain and range with a graph, we actually want to talk about graphs and if they are functions or not. Because all graphs are relations, because all graphs, you can write the points as ordered pairs. But the question is a graph a function? It is if it passes the vertical line test. So remember, the vertical line test just says if every vertical line intersects your graph at no more than 1 point, then the graph is a graph of a function. So if you can draw a vertical line that passes through 2 or more points, it's not a function. So not a function, passes through 2 or more points, function at most 1 point. Let's look at example A. We want to state the domain and range for the relation, and then we're going to determine if the relation is a function. So this is where we can use the graph to find the domain and range. That's going to be a little bit tricky. Remember, the domain is going to be, oh, I don't want that, I want blue. The domain is going to be your x values. Now let me think about this. The x-axis goes from left to right. So if I pick any point on the x-axis, let's just say -10, does it correspond to some point on this graph? Yes. So if I go from left to right, and if all the x values correspond to a point on the graph, then that x value is in the domain. So again, all I'm doing is going left to right and seeing if it connects to a point on the graph. So now at 6, I'm actually crossing the x-axis, but then I go beyond x values that are larger than 6 and go up, I'm touching the graph. So in this case, again, this will go on forever because of those arrows, which means those x values will also go on forever and ever and ever, and my domain will be all real numbers or negative infinity to positive infinity. Let's look at the range. So the range is going to be our y values. And the y-axis is a vertical axis. It goes up and down. So I'm going to start at the bottom of my graph and I'm going to look at this 10. And I'm going to ask myself, does that y value correspond to anything on the graph? And yes, it does. So if the y value corresponds to something on the graph, then I can include the y value in the range. So if we keep going from bottom to top and go up the y-axis, you can see with this particular graph that every y value I'm picking corresponds to a point on the graph. Now if we go above, we're going to go towards the right, keep going, keeping in mind that this graph goes on forever and ever, and our range is also going to be all real numbers, which would be negative infinity to positive infinity. Okay, so is the relation a function? Well, it's a function if you have a graph. It's a function if it passes the vertical line test. So let's think about drawing vertical lines. Can I draw a vertical line that passes through 2 or more points? No. No matter where I draw my vertical lines, they will pass through at most 1 point. So I'm not going to keep drawing these vertical lines all the way across. You can see that this is a function because it passes the vertical line test. So it is a function. This is a function. Let's look at B. So we have this graph. This is the graph of an ellipse. It's kind of like a circle that's squished. Now I want to find the domain, which would be my x values. And I'm going to do what I did before. I'm going to pick x values and see if it corresponds to anything on the graph. I have a problem though. Notice that when x is -3, I have a point, but when we look at points that are, or x values that are smaller than -3, say like -4, whether I go up or down, I'm not touching the graph. I don't touch the graph until I reach x is -3. That is the very first time that I'm touching this graph at this point here, which is -3. So that's my very first x value. Now I can keep going and choosing different x values, and notice that they will correspond to the graph in at least 1 point. And I can keep going. I'll end up here at the end with a +3 for my x value. But when I look at x values that are larger than 3, I don't touch the graph, which gives me a domain of -3, but that's with a bracket because it's solid. It's including the -3. So the domain would be -3 to +3 with brackets because it is including that point. So now range, we're going to do the same thing. We're going to look at the y values. Well, when I look from below, what color am I going to choose? Do I want green? No. I'll do yellow. When I look below -2, doesn't correspond to anything on the graph. As I go up, the first time I touch the graph is with a y value of -2. And then keep going, you could see that inside this ellipse, I am touching the graph. At +2, I'm touching the graph. But anything larger than 2, and I'm no longer touching the graph. My range is going to go from -2 to +2 inclusive. So I'm including those values. Oops. I don't know why I can't write anymore. And the question is this a function? Not a function. And it's not a function because it doesn't pass the vertical line test. I actually drew a bunch of vertical lines that pass through 2 or more points. And in fact, when you just look at the y-axis, that is a vertical line that is passing through 2 or more points. So I can draw infinitely many vertical lines that pass through 2 or more points, so it's not a function. So let's say that you did have an equation and you wanted to figure out domain and range by graphing. In example 5, we're just going to sketch some simple graphs by doing a simple method called plotting points. Throughout this semester, we're going to be looking at a lot more complicated graphs. This is just looking at the techniques of plotting points. So we're just looking at simple graphs. When we plot points, the goal is just to get a bunch of ordered pairs so we can graph. Now in A, we have a function because it's f of x. So I know it's a function, not just a relation. F of x is equal to x plus 1. So this equation is actually written in function form. If the f of x bothers you, you can always replace it with y. Y equal to x plus 1. That's absolutely fine. So we're going to do our table of values. We're going to put in an x value and then we'll get back our f of x, which again, you can just write as y if f of x bugs you. So the point is to put in x values into our function. And since the graph that's given goes from -6 to +6, maybe I'll start with -6. Maybe I'll just do evens for now, see what happens. 0, 2, 4. That's a lot of ordered pairs. So if I put in -6 for x into my function, and then go back to this equation, -6 plus 1 is -5. So my y value is going to be -5. And I have my first ordered pair, -6, -5. If I put in -4 for x and add 1 to it, I get -3. So now I have another ordered pair, which would be -4, -3. And I recognize y equal to x plus 1. That's just a line. So if I put in -2 plus 1 gives me a +1. -2 gives me a -1. Sorry, can't do simple math. And then 0 for x would give me a 1 for y. I can clearly see this is going to be a line. And it's exactly what I expected it to be. So actually we are graphing that example equation, example 3b. So remember we had set builder notation where the relation was y is equal to x plus 1. So now I'm just graphing that to see if, did I get the correct domain and range? Let's see, 2 plus 1, that will give me 3. So if we continue on, I see 4 would give me 5 on the y. I can clearly see that this is just going to be a straight line through the points, and if I keep putting in x values, it'll go on and on in both directions. So looking at that graph, I can see by the picture that the domain I had before in example 3b was correct. My domain is all real numbers, and I can see that my range is all real numbers as well. Now in this particular problem, we were just supposed to graph our function by plotting points so we can review that process. It didn't ask for domain and range. Let's try another simple graph. This is f of x is equal to 2. Again, if the f of x bothers you, you can replace that with y. So this would be y equal to 2. And then we have our ordered pairs. We're putting in an x. We're getting back an f of x. Again, if that bothers you, you can write that as y. I will put in the same value since I have the same blank graph that starts at -6. I don't want to put all the values from -6 because that's just so many. I'll just do the evens for now. And then if I put in -6 into my function, notice that, going back to the equation f of x equal to 2, the 2 doesn't have any x by it, so it doesn't really matter what I put in for my x value. This function is always just equal to 2 because y is equal to 2. It doesn't matter what x value you have, your y value is always equal to 2. So it's always -6, doesn't matter, y is 2. -4, doesn't matter, y is 2, and so on. We have our ordered pairs. Now it's -6, +2, -4, +2. And we could just plot all of these points all the way across and draw our graph. So this would just be the horizontal line, y is equal to 2. So again, all we're doing is just reviewing how you would plot points. Now the disadvantage to plotting points is maybe we didn't get enough points to get a complete picture of what the graph is. So now the last thing we're going to do here, or almost the last thing we're going to do, is we're going to be using that function notation. So we use the function notation when we graph by plotting points, even though I did replace the f of x with y. But now in example 6, we are not graphing. What we're doing is we're going to have a function, and then we're going to put in different values for x into our function. Example 6, we have this function, and we want to find f of x for the given value of x. Part A, our f of x is the function x squared plus 1. So what we want to do is we want to evaluate this when x is equal to -1. So think about what this function notation means. It says that I'm going to put in, it's just a substitution, I'm going to put something in for x. And then for this particular function, we're going to take whatever that is and we're going to square it. And then we're going to add 1 to it. We have to be careful when we're putting in negative values, though. We have to be clear about where our parentheses are. So remember, x in this particular function, that whole x value is squared. So when I put in -1 for x, I'm taking -1 and squaring it, and then I'm adding 1 to that. So that's going to be equal to 1 plus 1. And then my answer would be 2. So f of -1 is equal to 2. We're going to use that almost same function in b, except for notice the difference here. It's a -x squared. Now the negative is not, the negative x is not in parentheses. The negative is outside of the x. So you have to be very careful and very clear that what I put in for x here does not include the negative, because this is the same as -1 times x squared. So that negative is not included with that square, that exponent 2. This time when we put in -1 for x, it's going to be f of -1 is -1 squared. So the negative stays, and -1 squared is +1. In this case, f of -1 is 0. So slight difference in A and B. So just be careful about the negative, especially in front of a variable x with an exponent other than 1. We'll move on to a couple more examples. And C and D, exact same function. In part C, we want to put in 0 for x. So f of 0 is equal to the square root of 2 times 0 plus 4. So 2 times 0 is simply 0. This is the square root of 4. And that would be 2. So f of 0 is equal to 2. Same function, but this time we're putting in -2. F of -2 is equal to the square root of 2 times -2 plus 4. So that's going to be the square root of -4 plus 4, square root of 0. So just remember, the square root of 0 is not simplified. Square root of 0 is 0. So f of -2 is 0. We don't have to put in numbers though for x. Example 7. We have this function, f of x equal to 2x minus 7. And we want to find f of a, f of 2a, and f of a plus 1. So I already have my function. What is f of a? So this function, f of whatever I put in, is equal to 2 times whatever I put in minus 7, which means that f of a is equal to 2 times a minus 7, which is simply 2a minus 7. But f of 2a is equal to 2 times 2a minus 7, which is 4a minus 7. So you do have to write things in the simplest form. And then when we put in a plus 1, we'll have f of a plus 1 is equal to 2 times parentheses a plus 1 minus 7. Distribute the 2 to get 2a plus 2 minus 7, which is 2a minus 5. Okay, so again, not only can we put in real numbered values, but we can also put in variables into our function. The last thing we're going to look at in this section is finding the value of a function if all you have is a graph. In example 8, we have this graph, and we're asked to find f of -2, f of 2, f of 0, and f of 4. So remember that in the parentheses, these are our x values. So we're saying, okay, for the x value of -2, what is f of -2? What is the y value that goes with that? So this first f of -2, I'm going to go to -2 on the graph, and then I'm going to go down to where the graph intersects at this point, and the y value that goes with an x value of -2 is -4. So f of -2 is -4. What is f of 2? So we go to the x value of 2, we go down to the graph, and we figure out what y value goes with an x value of 2. And that would be a y value of negative 2. F of 0. At 0, I go down, ooh, what is that? I don't even know. I have to estimate this one because it doesn't follow on a grid. So it looks like it's halfway between negative 2 and negative 4, so probably a negative 3. That's the disadvantage of finding values by just looking at a graph. What about f of 4? So I go to f of 4 and I go down, and again it's a halfway point between 0 and negative 2. So f of 4 looks like f of 4 is negative 1. Let's try another example. In example 9, we have a graph, and we want to find f of negative 4, f of negative 2, f of 1. Now look at this graph. It's kind of broken up. So something that happens with graphs, I'd like to remind you that when we have something like this open circle down at the bottom of our graph, that means we do not include that point. But when it's a solid dot, it means we include that point. So the question is, I'm using function notation, but is this a function? The answer is yes. It does pass the vertical line test. Think about the only place where I would have a problem would be looking at the y-axis. If I draw that vertical line, does it pass through 2 or more points? No, it only passes through 1 point because the other point is an open circle. It's not included. So actually, yes, this does pass vertical line test. It is a function. It's a special function called a piecewise function, which we'll look at later on in this course. However, that's not part of this problem. What we want to do is we want to find f of negative 4, f of negative 2, and f of 1. So f of negative 4 says we go to negative 4, which would be, it looks like since this is a negative 5, on this particular graph, not every tick mark or grid mark is labeled, but I can tell that since I have negative 5, that I have 1, 2, 3, 4, 5, that negative 4 must be right next to negative 5. So if x is negative 4 and I go to my graph, I get a y value of, again, we have 1, 2, 3, 4, 5, so I have a y value of 2. The next one would be f of negative 2. If f is negative 2, so that would be at this second tick mark from the origin towards the left, I go down on the graph and I have a corresponding y value of negative 1. If f is 1, I go to 1, or if x is 1, I go to 1 and it looks like it's 0. All right, so that is it for this section.